or two communications to all of you and those who are not joined. So we want to start the program exactly what time we have specified, okay, so that it will be easy for the expert because experts are very busy. So they kindly concentrate to be give the lectures. And also, I have written to all of you that all the lectures are interconnected, so that if you, attend all the lectures, you will be benefited because this is totally done on philanthropic mode, all this kind of training program. And we are very fortunate that the best expert in this region we are having, and they will be sparing their time. This is a training, we have started from very beginning. Those who are not exposed to meteorology much, and also those who have already working in this kind of meteorology and agromet services. That's why first two lectures will be on the fundamental, then we'll be going to the main course of the program, training program. So my appeal to all of you that please don't miss any class, because you will all be benefited, by if you get. And we'll try from our part that to help you in all aspects. Even also what we are feeling that maybe at the end of this training we will be very casually will be evaluating how much you have benefited, and based on this we can remodule the session. So with this, I'll just start today's program. And today we are very happy that the expert who is with us, he is Dr. Somnath Datta. He is working number of years in India Meteorological Department, and particularly he worked a number of years in the training division of India Meteorological Department of Ministry of Arts, says Government of India. And um, and afterwards he became the head of the training institute, and subsequently he was the head, recently he retired from India Meteorological Department regional office head from Kolkata. And uh, Somnath Datta, he is a perfect person who is today giving the lecture. And in addition to that, he is at present, he is a project manager, development of skilled manpower in arts system science, called DESK, in Indian Institute of Tropical Meteorology, Ministry of Arts Science, and he is a retired scientist of India Med Department. So we are very happy to get him today's lecture. So over to Dr. Somnath Datta. Over to you.
Thank you very much for a few kind words about me. First of all, I am extremely thankful and grateful to the organization, South Asian Forum for Agricultural Meteorology, for giving me an opportunity to showcase my very little skill, very little knowledge uh, among this so August gathering. So, so with this, now I will start my lecture. I am now sharing the screen.
मोबाइल यहाँ देऊ अर्कै भाइब्स आउँछ हो मोबाइलसँगै भयो भने
Yes, Somnath, we can see. Yes.
Okay, thank you very much. So actually, I have divided my talk into two parts. Uh, the topic is name is same, a few basics of meteorology. In the first lecture, I will discuss basics of some thermodynamical aspects of the atmosphere, and second part I will discuss the dynamical part and some weather system. So we all know very well that our atmosphere is divided into a few layers: troposphere, stratosphere, mesosphere. All these things we can see, and we are in the troposphere. When we say the atmosphere, then mainly we mean the troposphere itself. And in the atmosphere, there are a ocean of a mixture of gases. Many gases are there. It is there actually: nitrogen, oxygen, argon, water vapor, carbon dioxide, methane, nitrous oxide, ozone. You can see some of the name, it has been highlighted actually. So these are important for some other purpose actually. Greenhouse gas, you all know very well. So maximum contribution is from nitrogen and then followed by oxygen. So, so this is there. Uh, Now, so as we are telling that we are mainly interested for the troposphere, it is the lowest layer of the atmosphere. Most of the mass is in the troposphere itself. Most types of clouds are also here. And it is by far the wettest layer of the atmosphere. And here air is warmest at the bottom of the troposphere near the ground. And air gets colder as one rises through the troposphere. And air pressure and density of the air also decreases with altitude upward to the up to troposphere. And troposphere is treated as the boundary. It is the tropopause is the boundary between troposphere and stratosphere. And now, first thing is variation of pressure with height. Atmospheric pressure, actually, we define at a point as the weight of air contained in a column. Cross section of the column is just unit, and that column is extended from that point up to the top of the atmosphere. And mathematically, it can be expressed like this: that if I consider a small slice with thickness dz and cross section 1, then volume of that small slice will be equal to 1 into dz. And if the density is rho, then mass will be rho into dz and weight will be this. And our entire atmosphere consisting of infinite number of such slices from surface, from that level where we are considering the atmospheric pressure up to the top of the atmosphere. So it is expressed in terms of the integration. And from here we can see very well that if I increase the value of H, then the value of the pressure will be decreased, and which I have shown it analytically also. And physically also we can understand, if we go above, then the height of the column will decrease at the lower side. So therefore amount of the air contained in the column will be less, its weight will be less, so naturally weight will be less. Then thermal structure of the atmosphere. So entire atmosphere, as I told you, that is, we all know very well, it is divided into a few layers: troposphere, stratosphere, mesosphere, and thermosphere. It is written here. In the troposphere, temperature decreases with height, because it is reasoned like this, that in the troposphere, main heat source is not the solar insolation, rather the outgoing long wave heat radiated by the Earth's surface. So therefore, Earth's surface is the main heat source. As we go away from the heat source, so naturally that heat received will be less, accordingly temperature is less. And in the stratosphere, again, we can see there is an increase of the temperature. This is being attributed to the presence of the ozone, which absorbs the ultraviolet ray of the solar insolation and becomes another one source of the heat energy. So therefore, in the stratosphere, temperature increases with height, and mesosphere again it decreases, but in the thermosphere it is increases with height. Thermosphere. And but all weather phenomena takes place in the troposphere, also, troposphere mainly. Now, Basic thermodynamic variables are our pressure, temperature, and the volume. And thermodynamic state of a system, it is specified by these three quantities only. Uh, However, they vary with each other under different conditions. We all know Boyle's law, which says that volume varies inversely with pressure under isothermal condition. Charles law also we know that volume directly proportional with the temperature under isobaric conditions. So when both neither isobaric nor isothermal condition prevails, then in that case all these three varies and they varies following this law. That is pressure into volume divided by temperature, it remains constant. And this constant, we all know, this is called universal constant, universal gas constant. Okay. So now if we consider a gas of mass m at temperature T and pressure P and volume V, the molecular weight, if the molecular weight of the gas is capital M, then number of moles present in this gas, it will be is equal to mass of the gas divided by molecular weight of the gas. So if we say this is equal to N, then the equation of state, it may look like this. PV is equal to, because this PV is equal to RT, this equation is mainly for 1 mole of gas. So if this many number of moles, it will be like this. And if we simplify, we will get this equation P into alpha is equal to R star into T. This alpha is nothing but volume per unit mass, which we call in our meteorology specific volume, and R star we call the specific um, gas constant, specific gas constant. But anyhow, whatever equation we see, this is for a gas, single gas only. But as we have seen that our atmosphere doesn't consist only a single gas, rather it is a mixture of gas. So for the mixture of gas, we are having different way of telling. It is like it is described here itself. If we consider a mixture of n gases which don't react each other chemically, and if the partial pressure of the ith constituent gas is Pi and total volume is V, and the mixture of the temperature of the mixture is T, then our equation of state for the ith constituent gas will be like this: Pi, that is pressure, into volume divided by Mi into R by Mi into T. It is like this actually. We take from here. That's what. Okay. So therefore, if I take the sum, if we take the sum, then we will get this equation V, then its sum, and then we will get Mi by Mi, is a simple mathematical calculation, and ultimately we will get this equation P alpha is equal to R divided by M bar into T, where if 1 by M bar is given by like this, that is summation of individual mass divided by individual molecular weight divided by total mass. It is 1 by M bar. This M bar is called mean molecular weight. In that atmosphere, there are many important thermodynamic processes are there. Many we are knowing also, just like one is isothermal process where temperature does not change. Uh, During phase change of water substance, this happens, isothermal. Then isobaric process where pressure does not change. Then another one is your adiabatic process, very important, where no heat is added to or no heat is extracted from the system. And then again, this adiabatic process can be for a completely dry gas, or it can be for a mixture of dry air and the water vapor. That is, so therefore, accordingly, we are having two different type of adiabatic process. One is a adiabatic process for the completely dry air, which we call dry adiabatic process. Another one, adiabatic process, which is the adiabatic process for a mixture of dry air and the water vapor, which we call moist air. That is called moist adiabatic process. Besides, there are some important processes are there. That is that we know very well. One is your saturation, one is your condensation, then evaporation, then heating and cooling. Heating and cooling also, saturation we all know very well. If we consider a closed vessel which is half filled with water, then the free space above the water, we know there will be dry air as well as there may be some water vapor. And thermodynamics says that under this condition, under this condition, there will be transformation of water molecule into water vapor molecule, and the vice versa. That is water vapor molecule into liquid water molecule. Okay. Now, rate of conversion of either of these two depends on the temperature of the air in the free space over the liquid surface. Initially, we all can understand that rate of conversion from liquid to water vapor molecule will be more than from water vapor to liquid. But at some time equilibrium will reach when both the rate will be same. That means when that rate of transfer of liquid water molecule to water vapor molecule will be same as rate of transfer from water vapor molecule to liquid water molecule. And then we say that saturation stage has been reached. This we all know very well. And what happened? What does it mean? That free space is now contained with the maximum amount of water vapor. Beyond that, it cannot hold it actually. Again, this holding capacity of the air, holding capacity of the air, holding capacity of water vapor by the air, this also again depend on the temperature. If the temperature of that free space is more, then holding capacity will be more. So, but whatever it may be, given a temperature, it has a holding capacity, moisture holding capacity. Now, if you give more moisture there, water vapor there, then it may not be able to hold it. So immediately it will be converted to water, to the liquid water. That means which we call condensation. So this is very much happening in our atmosphere. We know very well, and similarly evaporation also taking very much happening. Just like when cumulus cloud is there, CV cloud is there, when cirrus anvil is there, there is evaporation of the cloud liquid water is taking place. Okay, and due to evaporation, cooling takes place, and due to condensation, heating takes place. So that's why heating and cooling also another one important thermodynamic process. But heating cooling can be done diabatic way. Diabatic means sensible or latent. That means heating due to solar insolation, it is your sensible, and due to condensation or evaporation, heating cooling, that is your latent heating. Another one way of heating cooling is also there. That is your, if there is expansion or compression, then also some heating and cooling is taking place. That is your adiabatic heating and cooling. So these are the different thermodynamic processes in the atmosphere. In the thermodynamic, there are another very important, that is reversible thermodynamic process, irreversible thermodynamic process is also there. A thermodynamic process is reversible if after performing a change, if this can be reversed. Theoretical definition is that if each state of the system is in equilibrium, so that reversal in the direction of an infinite change, return the system same way actually. For example, dry adiabatic process, it is a reversible thermodynamic process, wherever moist adiabatic process is not a reversible adiabatic process. Pseudo-adiabatic process is not a reversible process. We will see pseudo-adiabatic process later. Then in the thermodynamic, atmospheric thermodynamics, another one important element is there, that is specific heats of gas. Gas is having two specific heat. One is your specific heat at constant pressure, another one specific heat at constant volume. It is very specific heat. You all know very well that it is the amount of heat required to raise the temperature by unit. So now, if certain, if I want, if I keep the volume does not change. If I say that if we put the constant that gas is not allowed to be expanded or compressed, that means I am not allowing to do any work by the gas or on the gas. So therefore, whatever heat we will give to the system, entire amount will be utilized for increase in the temperature. So therefore, for increasing in 1 degree centigrade of the gas, some amount of heat is only there. But now, if you remove that constant, rather you put pressure is constant, that is only a constant pressure, then due to this constant pressure, gas is allowed to expand, gas is allowed to compress. So therefore heating cooling is possible. So therefore if you therefore amount of heat required for 1 degree centigrade increase or decrease of the temperature, it will be more than the other one, because here whatever heat you will take, entire thing will be immediately not utilized for the change of the temperature, because certain amount will go for the expansion of the gas. So therefore, you have to provide the heat until the temperature increases by 1 degree. So therefore, naturally in this case, amount of heat required to raise the temperature by 1 degree centigrade, it will be more. As a result of which, we can understand that specific heat at constant pressure is more than the specific heat at constant volume, and mathematically also it can be shown that their specific heat at constant pressure is more, and their difference can be shown to be equal to R, that is universal gas constant. Cp minus Cv is equal to R. Then come to the laws of the thermodynamics. So zeroth law we are not taking, we will discuss about the first law and second law. First law statement is very simple thing. If certain amount of heat is given to a thermodynamic system, then that heat can be converted into mechanical work. That is the simple thing. Heat can be converted into mechanical work. So mathematically it says that it is if certain amount of heat is given to a system, then a part of it goes for increasing its temperature. Sometimes we say the internal energy, and remaining part goes for doing some external work due to expansion or compression, due to change in the volume. So mathematically, we can say dq is equal to Cv dt plus P d alpha, where dt is the change in the temperature, d alpha is the change in the volume. So first law simply says that heat can be converted into water. That's all. But second law gives a limit actually. Second law simply says that that for heat to be converted into mechanical work, you require one source of heat at some higher temperature and a sink of heat at a lower temperature and an engine working between them. And in this process, entire heat energy cannot be converted into the work. Certain amount of heat energy will be unavailable for conversion into work. And this unavailability is due to the randomness or disorderness of the system itself. And this is expressed in terms of another one quantity we all know very well, we call it entropy. In any case, absolute entropy we cannot measure. However, change in entropy, it can be measured. And the change of entropy is defined as the amount of unavailable heat, which is equal to dq, divided by the temperature. Next is moisture in the atmosphere. This is very, very important. We all know very well, atmosphere is not a completely dry, it is moist itself, it contains water vapor. So So main thing is we need to measure the water vapor. So water vapor may be measured by couple of quantity. The first one is mixing ratio. Very simple thing. If a sample of air contains certain amount of dry air with of mass md and certain amount of water vapor mass mv, then mixing ratio is very simple. That is mv divided by md. That is mass of the water vapor divided by mass of the dry air, and you may express it in terms of percentage also. Then only you have to multiply by 100%. This is number one. Another one way that is very popular, that we may express the amount of moisture in terms of specific humidity. Specific humidity is nothing. It is also a ratio given by, it is a ratio of the mass of water vapor to the mass of the total air. So this must be is equal to mv divided by mv plus md. This is very popular. And another one is also there, water vapor pressure. Water vapor pressure, it is same way air pressure only. It is the pressure exerted by the water vapor on the surface of water in contact. It is the weight of water vapor in a column of unit area of the water surface. We know very well. Then saturation, condensation, already I have told. I need not to discuss it again. And relative humidity, we can define in three ways. That is, so we can understand one thing, that at the saturation, mixing ratio is maximum. I hope you all will appreciate this fact. Mixing ratio will be maximum. At the saturation, specific humidity will be maximum. And at the saturation, water vapor pressure will be also maximum, because at the saturation, mv is maximum. So therefore, suppose if I say that mixing ratio at the saturation is Ws, specific humidity by Qs, and water vapor pressure by Es, then relative humidity is expressed as actual observed mixing ratio by the saturation mixing ratio into 100%, or specific observed specific humidity, or saturated specific humidity into 100%, and similarly for the vapor pressure. So these are very important quantity. Many times we mention this quantity. Okay. So therefore acquaintancy with all this thing and skill for measuring all this thing is required. What I was telling, that another one very important parameter in atmospheric thermodynamics is potential temperature. So for defining potential temperature and understanding potential temperature, we consider a dry adiabatic process. Dry adiabatic process means we consider a sample of completely dry air. There is no water vapor. Okay, and for adiabatic process, you that dq, that is amount of heat, is equal to 0. So now, if you remember the first law of thermodynamics, you can see this first law of thermodynamics. If you put dq is equal to 0, dq is equal to 0, dq is equal to 0, then if we integrate this equation, actually, if you integrate this equation from 1000 HPa up to any pressure level, then you will get one equation like this, actually. In any case, will you allow me to use the board? Sometime it will be, or it will taking too much time. Okay, let me forget it, actually. This is with the first law of thermodynamics, and from the first law of thermodynamics we will get this one. And if it is integrated, that only I was telling, from an arbitrary level to 1000 HPa, then we will get one equation like this. And in this equation, all other term we can understand, only theta we don't know. Theta is the potential temperature. So potential temperature, physically it can be explained in this way. You consider arbitrary pressure level. Let us consider 500 HPa level. I want to find that 500 HPA level. For that, what I have to do? I have,
Somnath,
yes,
Somnath, you
yes.
can use the board also if it is legible here.
Oh,
You
what?
can use. Yeah.
Very good, very good. Thank you very much. Actually, this is very much required. Uh, so we have seen from the first law of thermodynamics that dq is equal to cv dt plus p into d alpha. This we have seen. And from the equation of state, we know P alpha is equal to RT. So if I take the differential, then you will get, if I,
Somnath, we cannot see your board.
oh, acha, acha. You cannot see your board, no? Just a
I think
minute.
you can continue like that. Hmm.
Just a minute, just a minute. Google. Okay, board you cannot see, no? Acha. Hmm. There is some problem. Let it be
No
then.
issue. No issue. You continue. Okay.
Acha, acha. Sorry, actually.
No issue.
So no, what I was discussing, just suppose if I want to know what is the potential temperature, say at 500 HP.
Somnath, your slide is not visible. Presentation.
Okay,
Yeah.
just,
Again, you.
just a minute.
Yes.
So if I want to know the what is
No,
the
Somnath, we can't see. We can't see. It has come again. It has gone.
why it should be just a minute.
Now it's okay. Now it's okay. You can make. Yes, it's okay now.
Okay, now,
Yes.
now,
Yes. Yes.
Yes, okay, okay.
okay. So what I was thinking, suppose if we want to know what is the potential temperature at 500 HPA, so for that very simple thing, I have to take one air parcel, what's a one sample of air of 1 kg mass, which is completely dry, and their air parcel, the pressure of that air parcel, I have to increase up to 1000 HPA without adding any heat or extracting any heat from it. I mean, we have to bring it to 1000 HPA level, dry adiabatically, and after it reaches 1000 HPA, then I have to check what is its temperature. And that temperature will be the potential temperature at 500 HPA level. Without equation, we can understand in this way. And potential temperature increases with height. This is very much visible, very much evident from the equation itself and from the physical consideration itself. Suppose same exercise if I do for 200 HPA, then in that case, more compression is required for an air parcel which has been taken from 200 HPA to bring it to 1000 HPA as compared to that from 500 HPA. So more compression means more heating. More heating means more temperature. So quite natural, we can understand from intuitively also that potential temperature in general case increases with height, and which we can see in our T5 diagram also. And another one important property of that potential temperature is there, that in a dry adiabatic process, potential temperature does not change with time. It is a conservative quantity. Okay. Then come pseudo adiabatic process and saturated adiabatic process and equivalent potential temperature. So for that actually, let us consider one moist air parcel from surface. Okay. And as the moist air parcel is heated, the surface, this moist air parcel rises above, rises up, and as it rises, then then it cools, and as it cools, the moisture holding capacity of the air parcel reduced, and as a result of which it gets saturated, that is water vapor, air inside the air parcel becomes saturated with the available amount of water vapor, and after that condensation takes place. Up to this it is fine. After that there can be two way out. One is the further rise of the air parcel can be. Now question is, when condensation takes place, two things happen. Two products we got actually. One is due to condensation, liquid water droplet has been produced, and due to condensation, certain amount of latent heat has been released. Okay. Then after that, further rise can be of two way. One way is that further rise can be along with both the product. Both the product. Then we will call it is a saturated adiabatic process. I am calling it saturated because air is in contact with the liquid. That means it is saturated. Adiabatic because I am not taking away any heat or giving any heat. Another one process is that after the condensation takes place, liquid water produced due to condensation, it is left, and the air parcel rises further. This is a pseudo-adiabatic process. This is a pseudo-adiabatic process, and this pseudo-adiabatic process, it is a irreversible process which I was discussing there actually. So, so this only it is written there now. Now, if we consider a pseudo-adiabatic or a saturated adiabatic process, in any case, saturation has been taken place. Okay. So now, suppose if the amount of specific humidity, if the specific humidity, if the one thing is very very clear, that if the specific humidity is Q, then amount of water vapor in 1 kg of air is Q only. It's Q. So now suppose dQs amount of saturated water vapor gets condensed. So due to that, certain amount of latent heat will be released. So this will be L into dQs. The since it is released, we are not adding. So that's why this minus sign is there. So therefore, this we put it in the thermodynamic, first law of thermodynamics. And after that, if we simplify and if we integrate, ultimately we'll get one equation like this. So that means this quantity doesn't change in a pseudo-adiabatic process. If this logarithm of this quantity does not change, that means this quantity also does not change. That is theta into e to the power LQS divided by CPT. It also does not change in a pseudo-adiabatic process. And this quantity, we call it equivalent potential temperature. So we have the pseudo in the for pseudo adiabatic or saturated adiabatic process. This is a conservative property. It is known as equivalent potential temperature. As for dry adiabatic, but another one, and one thing is very important for theta e, that this theta e remains conserved in a dry adiabatic process as well as in a pseudo adiabatic process. So that's why theta E is much better quantity, much stronger quantity than potential temperature. And in the tropics, so it is very, very important. Equivalent potential temperature, it is defined as the temperature that it is, we can visualize like this. Suppose I want to know what is the equivalent potential temperature at 700 HPA. What I will do? I will take one sample of moist air of 1 kg mass at 700 HPA level. After that, you will allow that sample to rise up, rise up until the entire moisture inside that air parcel gets saturated and condensed, and the liquid water formed is fallen from the air parcel, so that that air parcel becomes completely dry. So you can understand, even though I have taken the moist air parcel at 700 HPA, but to make it dry, it might have gone at 300 HPA or 200 HPA or 100 HPA, even beyond that. But once it becomes completely dry, then we bring that air parcel, that dry air parcel, adiabatically. Of course, that adiabatical will be a dry adiabatical only, dry adiabatically to 1000 HPA. And then we will measure the temperature. That temperature will be the equivalent potential temperature at 700 HPA level. I hope I have been able to explain it properly, but I will be very happy if I may be asked to repeat again, no problem. And this equivalent potential temperature is very, very important actually. Very, very important. Suppose if we want to know whether the boundary layer is stable or unstable, for that, this profile, vertical profile of the equivalent potential temperature plotting is very, very important. If we plot the vertical profile of the equivalent potential temperature, then in case of an unstable planet, unstable boundary layer, you will find that initially the equivalent potential temperature is decreasing with height up to few height, and after that it increasing, and up to that height, that depth, this is the depth of that convective boundary layer. This is very important. Equivalent potential temperature is very important in the tropics. Then comes lapse rate. Then now, in case of lapse rate, very simple thing is lapse rate is the rate at which temperature decreases with height. We all know very well that in the troposphere, temperature decreases with height. That we know and we appreciate it also. But temperature decrease is not similar every time, because we have already seen that rising of a dry air parcel takes place in one manner, rising of a moist air parcel takes place in some other manner. So therefore, that rate of change of temperature with height, it may not be same. So accordingly, we are having lapse rate for a dry adiabatic condition and lapse rate for a moist adiabatic condition. And another one important, because to understand the lapse rate, another one thing also we have to understand, that is hydrostatic balance. You can see this picture I have done. This is your surface, Z is equal to 0, and this is the column extending from surface up to top of the atmosphere. So here I have considered one slice from Z is equal to Z0 to Z is equal to Z0 plus dz, and cross section of this column is unity. So So therefore, what is the volume of this one? This one volume will be is equal to dz only. So, so therefore, what will be the mass of this one and weight? So mass will be rho into dz and weight will be g rho into dz. So this rho, this weight will be working downward, working downward. Okay, and this weight is equal to, we know very well, that is the difference of the pressure between this, and this is equal to minus dp, which is very clearly it is derived in the equation. So we can see, and from there we can get one relation, that is dp dz is equal to minus 0. This is your hydrostatic balance actually. And lapse rate I have already told, and in case of a dry adiabatic condition, we can show following these steps of derivation that that lapse rate is in dry adiabatic condition, it is equal to G by Cp, and it is almost about 10 degree Kelvin per kilometer. So it is constant. But since our atmosphere is not completely dry, so therefore we need to find out what is the pseudo-adiabatic lapse rate. So pseudo-adiabatic lapse rate or moist adiabatic lapse rate also you can find out like this. So now from the intuitive discussion which I was discussed. Now in case of pseudo-adiabatic process, what you have seen? You have seen that once the condensation takes place, latent heat of condensation produced and liquid water droplet produced. But liquid water droplet has been left and the air parcel rises with the latent heat of condensation released. And to maintain the adiabatic condition, that heat we are not supposed to take away. So therefore, that heat will remain there. And what it will do, due to rising, whatever cooling is taking place, that is being partially offset by the heating due to this latent heat of condensation. So as a result of which you can understand that pseudo-adiabatic lapse rate will virtually be lesser than the dry adiabatic lapse rate, and it can be mathematically also expressed that pseudo-adiabatic lapse rate, which is equal to minus dt dz, which is equal to the dry adiabatic lapse rate divided by a quantity which is more than 1. That means definitely it is less than dry adiabatic lapse rate. Next is your ascent of air and stability and instability. Now in the atmosphere we discuss stability. How we discuss? We just displace one air parcel vertically. Vertically we displace, and then after getting displaced, we just see whether this fellow is able to come back or it is continue moving away. If it comes back, then we say it is stable. If it doesn't come back, then it is unstable. So like that, actually, this is the treatment we have done. We consider an air parcel, which is initially at surface. So the temperature of the air parcel is same as the surface. So now if it is displaced vertically upward, then it will reach to a new level after some time. And after reaching at a new level, there are 3 scenarios. One scenario is it will remain stand still at that new level. This is a neutral case. It may again come back from where it was displaced. It is a stable case. And it continue moving again away up. That is your unstable case. This we all know very well. So that only that if it moves upward, how it can move upward? if at the new level itself the air parcel finds itself warmer than the surrounding ambient air. So therefore up to that level, ambient air ambient air has been ambient air, what happened? Ambient air has been cooled at a greater rate than that by the air parcel. That means air parcel has also been cooled due to rising motion. Environmental air, that is ambient air, it has also been cooled by because at the upper level. But as at the new level, the air parcel is finding itself lighter, that is warmer. That means ambient air has been cooled more than the air parcel. That means cooling rate of the ambient air is more than the cooling rate of the ascending air. This we have seen. Then and cooling rate is nothing but the that is the lapse rate. This is nothing but the lapse rate. So therefore, if we want the air parcel to continue move upward, that is an instability case. In that case, environmental lapse rate, that is rate of decrease of temperature of the ambient air, must be more than the rate of decrease of temperature temperature of the ascending air. As air ascends, ascending air's temperature always changes either dry adiabatic layer or moist adiabatic layer. So accordingly, we have this condition actually. These are all written here actually. What I told, that is the same thing is written here. So it is stable if the it is unstable, as I was telling, that if the temperature lapse rate of the environment is more than the adiabatic lapse rate. Because as I told you, the temperature change of the air parcel, that is sample of the air, it follows an adiabatic. Now this adiabatic may be dry also, it may be saturated also. If it is dry, suppose if it is dry, D, then you can understand that gamma E is greater than gamma D. So eventually it will become greater than the gamma S also. So this is an absolute instability. This is an absolute instability. And if it is, if the air parcel is not dry, rather moist, then this will be not gamma D, it will be gamma E. So in that case, environmental lapse rate is more than the saturated adiabatic lapse rate, which does not guarantee that it will be more than the dry adiabatic lapse rate. So this is your conditionally unstable. So for conditionally unstable, your environmental lapse rate must be more than the saturated adiabatic lapse rate or severe adiabatic lapse rate, even moist adiabatic lapse rate, but less than the dry adiabatic lapse rate. And it is absolutely unstable if the environmental lapse rate is more than the dry adiabatic lapse rate, and it is absolutely stable if it is less than the saturated adiabatic lapse rate. Because if it is less than the saturated adiabatic lapse rate, then of course it will be lesser than the dry adiabatic lapse rate. So this is the my first lecture. Uh, First lecture. So I finished now my first lecture. So I will be happy if I may be able to give answer
Yeah,
to
you can continue the second one.
second one. So
Yes,
can I take 5 minutes? Just I want to take water.
yes,
Just
yes, yes, absolutely, yes. So I'm just taking that time till Datta is coming. One thing is that what he has mentioned. I don't know how many people are very acquainted with this kind of uh, concept like that. But what I will do that this presentation I will share with you. You can read all this thing and you can ask any question from that, because if you understand the fundamentals of meteorology, that will help very much in your agromet kind of thing, particularly the physical concept of agrometeorology. And also, this will also help you to write different kind of research papers or like that. So you need not to be aligned with the fundamentals, but if you in the background, if you have the concept of what is dry adiabatic, what is pseudo adiabatic, what is the lapse rate, what is the potential temperature, even also whenever you jump to the next level of your assignment, in the interview board, you will be very comfortable if some of the experts is asked some kind of question on the meteorology. So what I propose that I may share you that video also if it's possible. But maybe some of the people, maybe the concept is looking very comparatively hard. But nevertheless, you that will enrich your knowledge about the meteorology. And subsequently, in the next class, we will be going directly to the concept of the agriculture meteorology, where some of the key points what Dr. Somnath mentioned may be added to that. Okay. So we will try to make the uh, all the presentations very interesting, and so that you can take it on a very positive frame of mind. But one thing, I was just mentioning that I mean, I invited more than 110 people. So 70 people joined, and at present 60 participants are there. So I will expect, that I know there are some emergency cases are there, but you please try to attend from the next classes, because next class, will directly go to the concept of agriculture meteorology, and after that, very specific subject of the meteorology, like applied agriculture meteorology. Then we'll be starting actually after the concept of agriculture meteorology. Very important aspect will be that crop weather models. And the crop weather models is very popular throughout the world. Where we'll be describing you that how in-season forecasting we can make with the crop yield. And we will be discussing about the statistical model. We will be discussing about that DSAT models, and it will be very, very interesting. And I mean, after the your lecture, training, so you can excel to these particular areas and in your country, that how you can help the institute, you can help the government of your respective, that how you can forecast after planting of rice or wheat, or maybe any kind of crop, potato, how we can do. And this is a very emerging areas throughout the world we are working. So day by day, you will be exposed to different different angles of this agriculture meteorology. Even also, I mean, in the month first week of April, we will be requesting, the best scientists in the space world, and in the space who are working with the agriculture meteorology with the different signatures from Insight, Moody's, and Sentinel, whatever may be the kind of things are there. So, and they will explain that how the satellite data, which is available, free of cost, they can also tell you that which site you have to go, how to. Even also, it is not that, Mr. Dr. Datta is there. We will be having kind of rapport with the participant, with the experts. It's not like that. We end the training program and it will be like that. A continuous kind of linkages will be established, so that we want that in your country, so you will be one of the pillars, agrometeorology who can help. So be with us and try to attend most of the classes if you don't have any emergency business will like that. So thank you, Dr. Datta. Over to you again.
Thank you very much. So again, I will start my next one. This is visible, no? Visible, I think, no? Slide is visible, no?
It is visible, but make it full screen. Yeah.
So in this lecture, I will
No,
discuss.
we can see your presentation.
We can now here we will discuss a few dynamical aspects. Of before that, actually, first let us recognize the atmosphere is a dynamical system and what are the governing laws. Dynamical system is generally
Somnath, we
yes.
cannot see your presentation.
Oh, why? Achha.
Again, it has gone. Yeah, make it full screen. Okay. So
Is it okay?
no, it has again. So you whatever earlier slide, you can continue with this.
No,
Again you go to the presentation.
no,
No,
not
no.
so. Just a minute. Mm,
Yes, yes. Yes, right. Yes, right. Continue.
fine, fine. So I so atmosphere is a dynamical system because atmospheric condition changes with time following certain physical laws, and these physical laws we all know very well. These are nothing but your conservation of momentum, mass, energy, water vapor, and the gas laws. So, and these laws we know they are called the conservative governing laws actually, and each laws are expressed in terms of some equation, and which when we solve it using the initial condition provided by the at different type of atmospheric observation system and different analysis scheme, then we are able to tell about the future value of temperature, pressure, density, water vapor quantity, water vapor content, that is specific humidity, then wind speed, direction, all these things we are able to tell. And then by setting up suitable functional relationship between these variables with the specific required weather, it is possible to tell about the future condition of the weather at a place at a time. So, so that's why our atmosphere is a dynamical system, and these dynamical systems are governed by a set of physical laws which are known as governing laws, and all the governing laws are expressed in terms of equations, and those equations are known as governing equations. Next come, what are the different major forces in the atmosphere? In the atmosphere, there are certain major forces are there. First one is frictional force or viscous force. We all know very well, whenever there is a motion, there is a self-adjusting force is there, which always try to slow down the motion. That is your viscous force. Then another one force is there, that is your force due to universal gravitational attraction. This is also there. This is important force. Then another one important force is force due to the spatial variation of pressure, which I tried to explain this way. We consider 2 points A and B, where pressure is equal to PA and PB. And then we join this line 2 point AB, and taking this line as axis, we just constructed one right circular cylinder with unit cross section. And then due to the pressure PA, what is the force on this space in this direction, the PA, and this will be equal to PB. So therefore, what is the net force in this direction, in the direction of AB? So we can understand this is equal to PA minus PB, and we can understand this will be equal to 0 if and only if PA is equal to PB. So what does it mean? That if there is a spatial variation of pressure, then this spatial variation of pressure gives rise to a force which we call it pressure gradient force. And it has certain property that, first of all, this force acts from high pressure area to low pressure area. And this pressure gradient force is perpendicular to the isoburst, that means line joining equal pressure. And next, another one force is your Coriolis force. It is due to the rotation of the earth, and that also for a moving object. So it is like this, that if a plane is rotating, if a actually reference frame, we say actually, if a reference frame is rotating, and then if in this rotating frame, if an object moves in a direction, then the movement of the object is affected by a deflection to the right, or rather in the direction perpendicular to the direction of motion. This is in the left, northern hemisphere. Right hand side it is to the left. So therefore, this deflection must be due to some force actually, and that force presents if the earth, due to the rotation of the earth only, and when the object is moving. If this force does not act on a stationary object actually, and this is your Coriolis force. And Coriolis force, its nature is to deflect a moving object to the right of the direction of motion in the northern hemisphere, and southern hemisphere it is left to the motion. And it is always perpendicular to the direction of motion. These are them. Then come your different types of balance. So we all know that in the atmosphere, different type of weather phenomena takes place. Starting from that your what is called what is called, I am forgetting the name, whirling wind, uh, what is called actually, it's tornado, thunderstorm, then your cyclone, depression, cyclone, then monsoon, then planetary scale wave. So all are not of the same, all are not having the same spatial dimension. We know tornado is a very small scale phenomena actually, very small. Tornadoes horizontal extension may be only a few kilometers, only a few kilometers only. Then then we are having thunderstorm, all these things. So it is of the order of 10 kilometers. Then we are having western disturbance, then depression, cyclone. These are all of the order of 1,000 kilometers. Then monsoon, planetary scale, that is 1,000 kilometer. Sorry, that is 10 to 100 kilometer. Mesos, it is 100. So synoptic scale weather phenomena, we all know very well. Synoptic scale weather phenomena, it is those type of weather phenomena whose horizontal spatial dimension is of the order of 10 to the power 3 kilometer. That is 1,000 kilometer. Vertical, do you know more? It cannot be more than 10 kilometer. So for synoptic scale or large scale weather phenomena, for horizontal motion, it is seen that the acceleration, frictional force, they are very small as compared to the pressure gradient force and the Coriolis force. Because one thing why I am telling all this thing, because you have seen that one of the governing law is momentum equation. And momentum equation will know this is nothing but your Newton's laws of motion. And in the Newton's laws of motion, left hand side acceleration is there, and right hand side different forces are there. Different forces are there. And what are those forces? Frictional force. We have seen important frictional force, gravitational force, pressure gradient force, Coriolis force. Now, if we consider the horizontal motion, then gravitational force will not be there. Okay. And now it has been seen that if we consider a large scale weather system, and that also in the mid latitude and even here also, for the large scale weather area, then it is found that the magnitude of the frictional force, magnitude of the acceleration on the left hand side, they are very much smaller than the magnitude of another two forces, that is pressure gradient force and the Coriolis force. So therefore, in the horizontal motion, for synoptic scale horizontal motion, there is an approximate balance is there between the pressure gradient force and the Coriolis force, and this balance we call it geostrophic balance. And from the geostrophic balance, what wind we results, this we call it geostrophic wind. And in the mechanics, actually, it is said that any motion which results from the balance of a two forces, that motion is along a straight line motion. Straight line motion. So therefore, geostrophic motion will be a straight line motion, of course, non-accelerated topward, because I have already and Coriolis force and pressure gradient force, they are balanced to each other. That means that they must be acting opposite to each other. Pressure gradient force, you can see, we have already seen it is perpendicular to the isobar. But pressure gradient force is already perpendicular to the isobar. So therefore, we can see that this flow is parallel to the isobar. Geostrophic flow will be parallel to the isobar. And since the flow is straight, so isobars also constrained to be straight. This is a problem actually in this geostrophic approximation, which we will discuss later. And geostrophic wind has certain properties. As I told, it is a result from complete balance between two forces. So it is a straight line flow. It is parallel to isobar, just I told you, and it keeps lower pressure to its left in the northern hemisphere. And as the magnitude of the pressure gradient force increases, the geostrophic wind also getting strengthened. Now, you have seen that in case of geostrophic approximation, it is a it is a balance between pressure between two forces. So therefore, as I told you, flow is along a straight line, flow is parallel to the isobar. So therefore, isobars are being constrained to be straight line, which is not so. Which is not so because we don't have any control on the isobar. So there is a problem in the geostrophic approximation. So so now there is some then another one concept is that is gradient balance. Gradient balance, it is also a balanced flow, but it is this flow is a results from a balance of three forces. What are those three forces? One is your pressure gradient force, of course, Coriolis force, and this flow does not say that flow has to be straight. Flow can be curved also. And for any curvilinear flow, we know that centrifugal force must be there. Centripetal force is there, that's a centrifugal force. So there are three forces actually, balance between three forces. And whenever there is a balance between three forces, such flow cannot be straight line. It is along a curvilinear path. But this flow is also parallel to the isobar. This is also non-accelerated. This is also frictionless. But only thing is, this flow does not constrains the isobar to be straight line. Isobars can be curved at all, but this flow of course constrains that isobars must be parallel to each other. Isobars must be parallel to each other because if uh, because if you want isobars not to be parallel throughout, then in that case sometimes distance between two isobars will be more, sometimes distance between two isobars will be less. What does it mean? That means during the flow, sometime pressure gradient force will be more, sometime pressure gradient force will be less. And if I consider the balance between pressure gradient force and the Coriolis force, that means geostrophic balance, then sometime to meet the higher pressure gradient force, Coriolis force has to be more, and sometimes to meet the reduced pressure gradient force, Coriolis force has to be reduced. And Coriolis force, as it is a product of the wind speed, that is wind speed and the Coriolis parameter, so therefore it demands during the flow, geostrophic wind must changes with speed. And if the geostrophic wind must changes with the speed, then I cannot say that geostrophic wind is I cannot consider a non-accelerated flow. Got my point? So therefore, this is also a limitation in this gradient wind approximation, because gradient wind approximation does not allow us for this one. That is confluence. In meteorology, we call it confluence and diffluence. When the isobars are getting narrowed, uh, narrowed, then it is confluence. That means when geostrophic wind is getting accelerated, and when they are getting apart from each other, then deceleration of the geostrophic wind. So gradient wind, so therefore we can see the gradient wind is nothing but it is also frictionless, horizontal, non-accelerated flow, and it's a balance between three forces. Gradient flow, we can divide into four types I have shown in the picture. One is your normal low, which is nothing but a cyclonic flow around a low. This I have shown here. Another one is anomalous low, anticyclonic flow around a low. Sometimes in case of tornado, water spout, this type of thing uh, can be seen. But of course, it might be smaller scale. Anticyclonic flow around a low, we call it anomalous low. Another one is a normal high and anomalous high. This is your anticyclonic flow around a high with higher speed or and lower speed. And gradient balance or gradient flow is better because it is a generalization of the geostrophy. From the gradient balance, uh, as a special case, we can get geostrophic wind when the curvature of the flow is very less, which is applicable in case of a jet stream. So that time actually gradient balance simplified into geostrophic balance. Cyclostrophic, that means when the Coriolis force is very negligible. In that case, the balance will be between the pressure gradient force and the centrifugal force, which you can see in case of a cyclone, anticyclone. And another one is your inertial balance, when pressure gradient is very weak, right? Then the balance will be between centrifugal force and the Coriolis force. Next is your turbulence. Turbulence actually, for agricultural meteorology, turbulence mainly, I hope that it is interested for the planetary boundary air turbulence, even though in the upper air also turbulence takes place, that is called clear air turbulence, but it is an aviation related matter. So that's why this I am discussing the turbulence in the planetary boundary layer. Planetary boundary layer we know very well. It is very adjacent to the Earth's surface, lowermost part of the atmosphere. It contains only 10% of the atmospheric mass, and maximum interaction between Earth's surface and overlying atmosphere takes place, and maximum exchange of the physical property accordingly takes place. This is planetary boundary layer. And this planetary boundary layer actually it is characterized by turbulent motion. And broadly, in qualitative sense, two types of turbulence may be there. One is your convective turbulence, which I have shown here. That is air parcel in contact with hot surface becomes hotted, warmer, positive wind goes up, and cold air comes down. So this is convective turbulence actually. And another one is a mechanical turbulence, which I have tried here. Suppose this is surface and this is planetary boundary layer, and here say mean wind. I have shown in terms of arrow. It is changing with height. That means there is some vertical shear. So now if this type of shear is there, then this will result in this type of wheeling motion. Wheeling motion. Wheeling motion is having this one lower line and upper line, rising line and sinking line. So rising line brings surface property to the atmosphere. This is atmospheric property to the surface. So this is your mechanical turbulence. now in the real atmosphere, it does not take place in an isolation. So both the things effect may be there. So that's why for the operational forecaster there is a thumb rule is there. They use Richardson number. This is a dimensionless number which determines whether the flow is laminar, turbulent, then non-turbulent or turbulent. If it is less than 0.25, then it is turbulent. In the planetary boundary layer, as I told you about the turbulent motion, but at the same time, in the planetary boundary layer also mean motion is also there. But only thing is in the planetary boundary layer that effect that both the mean motion and the eddy motion or turbulent motion needs to be quantified separately. And for that some method is required. And this is being done by a method called Reynolds averaging technique. Now Now in the atmosphere, many things changes. Temperature changes, humidity changes. So now mechanism of change of temperature. There are two way. One is your local effect and wind effect. Local effect is due to the change in the incoming solar radiation received at the surface, land surface. This is mainly controlled by the local heating, cloud and aerosol. You see, local heating or cooling results in increase or decrease in the temperature. Cloud, more we know very well, more the local cloud cover, more is the interception, resulting in a net reduction. Aerosol also, incoming solar radiation interacts with the aerosol, results into different radiative process like the absorption, emission, scattering, and this results in a net effect on the incoming solar radiation. Wind effect is also there. Wind is a carrier of the physical property. So if wind comes from a relatively warmer area to my place, then at my place temperature will increase. And if it comes from relatively cool area, then temperature decrease. So, and then another one is your warming or cooling due to expansion and due to compression and expansion. This is also another one. And humidity mainly changes due to wind effect. Now comes to some weather phenomena is there. That is first one is thunderstorm. Uh, this is it is a rain thunderstorm during thunder is heard since the thunder comes from the lightning. So all thunderstorms have lightning. It is a result of convection we know, and we call it severe when it contains hails 1 inch or greater and wind gusting in excess of 50 knots for a tornado. But there are certain necessary conditions are there for the thunderstorm development. First of all, strong surface heating should be there so that the air in contact with ground gets warmer. Second thing is availability of moisture water vapor. Why it is so? Because already we have heard the first lecture. Because if moisture is available, then my air will instantly become dry air, it will become a moist air. And you have already seen that moist air moist air gets buoyant quickly because its lapse rate is less than the dry adiabatic lapse rate. What do I buoyant? So that's why availability of moisture is a very good favorable condition. That's why relative humidity must be 75% above. And then instability, that must be instability. That means temperature decreasing at a steeper rate. Instability means I mean to say atmosphere must be conditionally unstable. That is environmental lapse rate must be greater than the pseudo adiabatic lapse rate. If it is greater than the dry adiabatic lapse rate, then the convection is confirmed. And another one thing is that even if everything is there, some lifting mechanism is there because we have to remember that very near to the surface, mainly at the subcloud layer, very near to the surface, the atmosphere is very stable. So, very stable. So, therefore, and this stable atmosphere, even though it is in a shallow layer, it actually resists any air sample to rise up. So, therefore, certain amount of work needs to be done against this resistance actually. Okay, to overcome this resistance, and I have to bring the air sample up to a certain level, which we call level of free convection, so that after that, that air parcel, sample of the air can rise in its own way. For that, some lifting mechanisms are there. So there are some lifting mechanisms are there, just like one is your orographic lifting mechanism is there. Large scale forcing is there. Large scale, suppose if there is a large scale convergence, that also gives rise to some rising motion, and then frontal upglide. For the thunderstorm, there are different stages are there. In the picture I have shown, one is your developing stage. It is marked by a CV cloud I have shown here. CV cloud. that is being pushed upward, continuous upward, you can see, upward by a rising column wave that is complete updraft. Cumulus cloud soon looks like a tower called towering cumulus as the updraft continue to develop. There is a little during this phase, either no rain or very little rain needed. In the mature stage, this can be divided into two parts. In the one part, there will be updraft, another one part, downdraft also takes place. Okay. In this stage, updraft continues and precipitation begins to fall out of the storm, creating a downdraft. And when downdraft takes place, at time cooling is also taking place and dryiness is also taking place. Dryness. Why dryness? Because when precipitation takes place, that means that whatever water vapor was there, that water vapor has been utilized for to condense to precipitate to rain. So therefore, amount of water vapor in the atmosphere has been reduced. As a result of which, that this side drying will be also there. Then in the decaying stage, there is no updraft. It is only downdraft is there. At this stage, a large amount of precipitation is produced and the updraft is replaced by the downdraft. And rainfall, of course, decreases in intensity, but lightning remains a danger. And these are the different high impact weather, strong wind, heavy rain, hailstorm, lightning, etc. Then comes cyclonic storm. From cyclonic storm, we call tropical cyclones. These are actually intense low pressure systems where maximum sustained wind exceeds 33 knots. And genesis generally, you can understand, it develops over that place where where your very much water vapor is available. Actually, it generally take a form over the warm tropical oceanic region away from the equator, where moist air converges and vertical shear is weak. And spatial extent, horizontal extent of a well developed tropical cyclone is from 100 kilometer to 1000 kilometer, vertical extension 10 to 15 kilometer. These are the classification. This we all know very well in the South Asian region. There are certain cyclogenesis criteria is there, that warm ocean water, that is sea surface temperature must be 26.5 degrees centigrade throughout as sufficient depth, that is at least of the order of 50 meter up to 50 meter below the sea surface. This temperature should be there. Relatively moist layers near the mid troposphere, that is up to 5 kilometers, there should be water vapor must be available. Certain amount, minimum amount of turning force is required. Actually, what happened, you can understand very well that due to low pressure, we can expect only convergence, and convergent motion is just a straight line motion. Therefore, some agent is required to make a bending, to give a bending to the converging straight line motion. And that quality, that virtue is only available with the Coriolis force, because Coriolis force has only the capacity to deflect the motion. So that for that actually it's certain amount of, a minimum amount of Coriolis force is required, and some pre-existing disturbance is also required with sufficient vorticity and convergence, and vertical shear should be minimum, and there should be convectively unstable layer. This is the horizontal structure of the cyclone. You must have seen many times this thing. That is eye, wall cloud, and outer region. In the wall cloud region, this is your wall cloud region. In the eye wall, we can say. In the eye wall, this updraft takes place. And then it falls here also and falls here also. And Here, here actually what happened? Compression takes place at the dry adiabatic rate. So at the I region, there will be some warming is there also. And I region will be cloud free. You can see here. So I wall cloud region, rain or spiral band. This is shown here, and the outer storm. This is your outer storm region. Schematic diagram from the satellite picture also you can see. This is I wall. Okay. Achha. Same thing as seen from a radar picture. Uh, Same thing only. I surrounded by 10 to 15 kilometer thick wall cloud. Height of the wall goes to 10 to 15 kilometer. Storm surge is associated with the cyclone storm responsible for 80% of the loss of human life occurs in the eye wall region. Actually, the exact position of this eye wall is identifiable with the cyclone detection radar, and the radius of maximum reflectivity of radar beam coincides with the radius of maximum wind in a cyclonic storm. So that's why in tracking, radar's role is very important. And the same thing in the horizontal structure. This is the vertical structure actually. First is inflow layer up to about 3 kilometers, where only inflow takes place. It is in the planetary one. Then middle layer is there, 3 to 7.6 kilometer, where mostly tangential with little or no radial component. That means no inflow. It is only just one, this one. And then is your outflow layer, where it is rotating in a clockwise, on an anticyclonic flow. Life cycle, it has formative stage, immature stage, mature stage, and the decay stage. Formative stage covers the period from the genesis to a cyclonic storm through pressure depression, deep depression stages. Then immature stage is that in the immature stage, central pressure of the system continue to fall till the lowest pressure is attained. Wind speed increases, usually at a distance of 30 to 50 kilometer. In the mature stage, no further fall of pressure is taking place. Increase of wind speed also doesn't take place. And decaying stage, tropical storm begins to lose their intensity when they move over the land, because for the tropical cyclone, the main energy source is latent heat. And that latent heat takes place due to condensation. And for condensation, actually water vapor flux should be there. And that water vapor, maximum abundant amount of water vapor can be fed into a tropical cyclone environment only when it is over ocean. Over ocean. So definitely when it goes to a land, so naturally that is cut off. So naturally decay stage takes place. Another one way is also there. Even it has not over the land, but if it has gone to a colder part of the sea, then also it happens. Because if it goes to the colder part, because what happens, moisture flux, that is transport of water vapor from the sea, from the ocean to the tropical cyclone environment, it depends on the temperature also. Temperature of the sea surface. Temperature of the sea surface. More, if the temperature of the sea surface is less, then in that case, moisture flux, moisture transport will be less. So if the moisture transport is less, you can understand remaining story will be also less. That is saturation, condensation will be less, latent heat of condensation will be less. So naturally energy will be less actually. Then this is actually physics and energetics of tropical cyclone. Total wind in a tropical cyclone can be separated into two parts. One is your primary circulation, another one second. This is your, in the tropical cyclone, we know very well this type of circulation takes place, isn't it? At the low level, this, and upper level, this outflow takes place. This is primary circulation. But at the same time, we also know, suppose this is I, these are this is your wall cloud region. In the wall cloud region, there is rising motion, then spreading, then sinking, then again this. And this is taking place both sides. That means it is what? In, up, out, out, down, in. This circulation is also taking place in a tropical cyclone. So this is called secondary circulation. Through this, actually, one thing is conserved, that is angular momentum, and through this energy is conserved. We all know very well Fujiwara effect. We all know, because in our region, so we know very well that when there is a twin cyclones, then only this phenomena takes place, Fujiwara effect. And these are some high impact weather phenomena. We all know strong wind, heavy rain, storm surge, lightning. Then comes in your syllabus, it is as waves in the atmosphere. Waves, we know it is a disturbance in an elastic medium. In atmosphere, waves may be seen, may be looked as a carrier of the physical property from one place to another one. And suppose if we have a wave with wavelength L, then we consider another one quantity that is called wave number. This is defined as 2 pi divided by the wavelength. Physically, it is nothing but number of wave with wavelength L which can exist around a circle of radius 1. So if the radius 1, then perimeter of the circle will be 2 pi into 1, that is 2 pi. So total length is 2 pi, and one wavelength is L, means one wave total length is L. So therefore, in the 2 pi length, how many wave will be there? That is nothing but your 2 pi by L. This is your wave number. For any wave, there are two things we talk. Because as I told, wave is a carrier of physical property. So it carries momentum from one place to another one place, energy also. So while carrying momentum from one place to another one place, at what rate momentum is carried, this we call phase speed. And the rate at which energy is carried, this we call group velocity. There are some waves where these two are same. Just like one wave is there that is called surface gravity wave. Shallow water, they are actually, these two are same. Okay, even Kelvin wave also like this. But there are some waves where these two are not same. That is, momentum transport and energy transports are not at the same. When it is same, we call such waves non-dispersive wave. And when it is not same, then we call it a dispersive wave. In the atmosphere, there are some major important waves are there, namely Rossby wave, gravity wave, then equatorial Rossby wave, Kelvin wave, mixed Rossby waves. This is there. Rossby wave, actually, it appears due to the change of the Coriolis force with latitude. Because Coriolis force is expressed as 2 into omega, which is nothing but angular velocity of the earth, into sine latitude into wind speed. So therefore we can understand that Coriolis force, of course, depend on the latitude. That means if air moves from one latitude to another one latitude, the Coriolis force acting, this will be different. So due to the variation of this Coriolis force, naturally there will be a variation in the pressure gradient force also. Due to that, some wave is generated, that is Rossby wave actually. And Rossby wave's phase speed is always westward. It moves from east to west. However, group velocity, that is energy propagation, may be east west or west east, and it is strongly dispersive wave. There are some fast moving Rossby waves out there. There are some slow moving Rossby waves out there, there are some quasi-stationary Rossby waves are there. When any Rossby wave whose wavelength is equal to some quantity, which is called critical Rossby wavelength, then such wavelengths, such Rossby waves are almost stationary, not moving. And any Rossby waves whose wavelengths are more than this critical wavelength, that is long at side, they are slowly moving. And and which are lesser than that, they are fast moving. Fast moving Rossby wave, their scope for vertical movement is less because they are being trapped. But the quasi stationary waves, they are most likely to propagate vertically, and they propagate as they propagate vertically, they transport energy, moisture, etc. Then another one important wave is Kelvin wave. This is equatorially trapped. That means these waves you can see near equator only, and it is eastward propagating wave, and it is non-dispersive. And these waves are excited by the tropical convection in the lower atmosphere, and they can propagate vertically. And gravity waves are there. They are also non-dispersive, but they can be eastward propagating also, westward propagating also. And internal gravity wave can propagate vertically upward also. And we finished my.
Is that what he has mentioned about the planetary boundary layer. Actually, we will be discussing more detail what is the impact of this kind of convective in horizontal convergence and mechanical convergence, that is horizontal, onto the crop, particularly sugarcane and others. And there we have a specific, lecture will be there. Two lectures will be there, micrometeorology, where it will be mentioned that how this planetary boundary layer is very very impacting the
Correct.
evapotranspiration,
Yes.
which will be very very important aspects. Even also that we'll mention about the Richardson number and real numbers, all like that. And another thing what he has mentioned about that different weather events. So we are having three lectures on the forecasting, weather forecast for agriculture. You will get the details what he has mentioned after that, how this phenomena is taking into consideration about the weather forecasting, and the best weather forecasting person will be there to give the deliberations. And also he has mentioned about the cyclones and other extreme events. So we'll be having another two aspects of how they will be connected to the meteorology, how the boundary wall is impacting more to the crops or like that. So whether next time any cyclone will be coming, you can visualize from that radar pictures and satellite pictures that your own estimation that what could be the impact onto that. I think that I mean today he has given a wonderful lecture. On that we have get all of you in the further lectures. So I'll be requesting all of you, if you can open your videos, we can take a photograph.
And any question is there, I will be very happy to.
Yeah. Another thing after that means picture session will be asking the questions. I'll be requesting all of you, please open your videos. Malti, can you take the photograph? Malti, can you hear me? Just wait, Malti. Malti, can you hear me? In the meantime, you can ask the question. Any question to Dr. Somnath Dutta? Take the picture, Malti. Okay. नहीं नहीं, जो भी है जितना हो रहा है, ठीक है ठीक है,
Actually,
okay, okay.
these
Sure.
dynamical aspects and thermodynamical aspects, uh, it is very difficult to cover within 1 hour as such.
Yeah.
Uh, so I know that whatever I told, this is very much incompleteness is there, but due to your time constant, actually, yeah, because there are a lot of discussions are there. I know lot of discussion. Even I have forgotten to mention one thing. In the extratropical latitude, one thing is there. Actually, in the extratropical latitude, there is one concept is there, air mass. Air mass, it is defined, it is the huge amount of mass. Huge amount of mass lying over a large region. Large region means of the order of thousands of kilometers. And for a long period means maybe 50 years, 100 years, and this thing. So now you can understand very well if certain amount of huge amount of air lies over some land, such a big land I am telling you, for more than many years. So naturally that air will acquire the properties of the surface over which it is lying, and this air will have a particular character. This we call an air mass. So once this air mass acquires this property from the surface, it becomes one type of air mass, and after that it starts moving. And this, now there may be two types of air mass. One, suppose for example, if some amount of, if huge amount of air lying over your tropical Pacific and all these things. So naturally, this, what will be the property of the air? It will be humid, warm, etc., etc. And at the same time, if this huge amount of air it lies over Arctic area, then it will be unstable, dry like this actually. So accordingly, we are having dry air mass also and warm air mass also. And when there are two air mass, there is a sharp boundary is there. And this boundary, we call it front. And front may be a cold front as well as a warm front is also there. Okay, so now in the extratropical latitude, there is also one type of cyclones takes place, which we call it. I am sorry, I forgot to include that here. That extratropical, that when there are two fronts, one front is there, cold front is also there, and both the fronts are moving in the same direction. And cold front, we can understand, cold front moves faster than the warm front. As a result of which, after some time, cold front catch the warm front and overtake. So at that time something takes place actually, and from that some types of cyclone takes place, and that is called extratropical cyclone. But these extratropical cyclone not necessarily to form over the land. So now question is, then where from it gets the energy? It actually, what happened, as I told you, extratropical cyclone forms in case of a cold and warm air contrast. When there is a cold and warm air contrast, this temperature contrast gives rise to the availability of one type of energy. And that energy is your called available potential energy. Now, this energy is being utilized for the development of the extratropical cyclone. And another one thing is there, that in case of the extratropical cyclone, that it is always a cold core cyclone, that is central is always cold. But whatever tropical cyclone, it is not like that. In the tropical cyclone, the main food is, as we have discussed, that is your latent heat energy. And extratropical cyclone, as just now I told, it is the available potential energy due to the temperature contrast between the cold air and the warm air. I forgot to include actually. So, if you are any question, I will be very happy to reply. Of course, these are very basic things. There is nothing very big things are not there. All of us we know. It's nothing there.
Actually, I do agree that 1 hour or 1.5 hour to grasp all this thing may be difficult, but this will give a such kind of concept. Even also, we will be sharing you this presentation with you, and maybe the video also. So, I mean, you can read out, and if you have any question, we can again connect to Dr. Datta. That's why I was telling that it's not like that. This is a lecture we have given, we finished. No, like that. We have to make a kind of linkages with all the experts so that you can, increase your
Yeah,
knowledge. But
that
again,
is,
before going to
you can ask
agriculture
any question,
meteorology,
madam. Take,
yeah,
take.
we can go to agriculture meteorology. These basics are very, very important. We feel that whenever you read more and more, just like Kelvin OX, Rosby OX, you will get that, and that will be very, very important for you. Any question is there?
Chottawardhan sir, I
Yes,
have just one suggestion, sir. Is
yes,
it
yes.
possible to make a Google Classroom? In the Google Classroom, if you create, then in the Google Classroom, any participants can put any question there addressing to concerned resource person. And concern, because what happened, this always happens in a classroom. Actually, many of us we may not like to ask a question there actually. Uh,
Okay.
so that's why in a personal channel, because in a Google Classroom, na, that question it goes in a personal channel actually.
Mm-hmm.
In a Google Classroom, there is a scope. For example, right now in front of me, one madam is there, Prathima. Suppose T. Prathima madam wants to ask some questions. She can simply put that question, and that question straight away will come to me. No one will be knowing that Pratima madam has asked this question, and I will have the scope to give the answer to everyone. So,
Mm-hmm.
so Google Classroom in the actually during COVID period when I was in IMD training, I used to do like this actually. You may think of actually just a
Hey, that is
suggestion.
wonderful idea. But in chat also they can ask the question straight away. You can answer, right? Okay.
Right
But
now,
yeah, right now.
now suppose
So,
what happened right now if anyone is not in a position to ask the question,
yeah, right. Okay.
for that only.
Right. We will do. We will do. So, if there is no question, then thank you to all of you, and thanks to Dr. Datta for the
Thank you.
wonderful this thing. And also, one request to all of you, those who has come from Bangladesh, then Afghanistan, Sri Lanka, and then Bhutan, Nepal. I request that you can communicate this message to others who could not join, and who joined but who was not at the end. Give the message that if they will be joined next time, so that will be wonderful, because number of experts, are their time, they'll be giving, sharing their knowledge to all of you. And maybe at the end of this event, we have connected to World Meteorological Organization. They were also attached to this training program, and we will be trying, if possible, to give the certificates to all of you. Those who will be presenting more than 75% of the classes, there are some norms are there. I think this kind of certificate will be very, very helpful for your career advancement. That is another side I am talking about. But literally, if you be there, then you will be enriched, because this kind of training to arrange, it takes a lot of time, lot of manpower. So we want that you people utilize this training, and at the end of the training, we are in touch, with all the director general and the director of agriculture. So they have all came to the inauguration session, and they themselves, even also the director of research of two agriculture university in India also. So they are very very interested. So they will also be, they said that they themselves will take that kind of initiative, that most of the participants will be there. So I'll be requesting once and again those who have joined still now. I mean, I'm very thankful to all of them, but they have another kind of this thing. They can communicate to this match rest of them, so that they can join from the next classes and make this training wonderful. Outcome will be there, we are expecting. And also we will be arranging some lectures from WMO also. WMO will also give how the different types of satellite data, different types of observation data can be retrieved, from WMO site. Even also, WMO will also give some kind of idea that how you people can be attached to the WMO kind of initiative, regional initiative. Because in this program is basically for South Asia, but WMO has divided full world into five regional areas. That is called RA2. In RA2 there are 37 countries are there. So they have a plan actually how this training is successful. Then they will go to Iran, China, and Korea, like that. Okay. So WMO is very very interested about this training, and so we'll be calling to them, and they will be also be attached to you for your kind of knowledge sharing or like that. So with these things, I once again thanks. If anybody has any kind of suggestions, raise their hands and they can tell. Or if not, they can send me in my email, so that we are always helpful to you in any aspects. Okay. Yes, Mr. Hossein Mubarak, you can proceed.
Thank you, Navansa sir. So regarding the training schedule, so I found it will be continued till 16, 19 March, 16, 17, and 19th March.
Yes.
So in Bangladesh, there will be the Eid vacation. So is there any possibility to reschedule it or not?
Because this training, we took 6 months to arrange, right? Okay. So and also the experts have been identified and do the thing. But one message has come from Afghanistan that in Afghanistan, they have been working on 9 to 2. So they said that the fasting end at 2, then they have a resting hours or like that. So they requested me if it can be done within 2. So that also I can do. But in your Eid, I mean, vacation in how many days?
It may be started from the 16 to 23.
16 to 23. Okay,
Yes,
okay. Of April, no?
March. This March.
March 16 to
Yeah.
20. Okay, you can just send a message to me. I'll try. Okay. Okay.
Okay, thank
Even
you.
also, even next class, I'll be rearranging from 12 o'clock. Okay. So that all Afghanistan people and other parts, they can join, and after that, they can go for that. I mean, their kind of activities or like that. Okay.
Okay,
And
Deputy.
16 to 23rd, I'll keep it in mind. I'll maybe reschedule that one. I'll try, like talking to the experts, right? Okay.
Okay, thank you, sir.
Okay. So if there is no question, then we can close it. And thanks to all of you for your uh, kind presence till end of this meeting. Thank you very much.
Thank you very much, sir. Bye bye.